right? Then plus some constant, because I'm just doing an arbitrary antiderivative over here. All right, that was our first example, so I put a 4 in there, and I'm sorry if it threw people off. I'm not ever going to do that again. It's going to be x from here on out, but I just wanted us to see we're really doing what we've done before in the past, except now we have to keep track of what's the variable and what's the constant. This becomes 1/16, right? So now what I do is I go back and I actually think, okay, well, wait a minute, hold on. This was really x, right? Which means, you know, this was an x, right? Let me put it in here. This was an x, which changes that to an x. And don't we have to scale by 1 over x, right? So there's a lot of things we have to kind of keep track of here, right? This becomes a 1 over x out here. This is a 1 over x out here. So I'm going to write the real antiderivative now, the real one, all right? It should be, you help me, -1 over x, because the 4 was the x, wasn't it? Y cosine of 4y? No, xy, plus, not 1 over 4, 1 over x, 1 over x, 1 over x squared, and then sine of, I just did it, xy plus c. Okay, that's the real antiderivative. We won't, now I'm going to go back, because remember, this was all scratch work. So now let me go back to where we were. All right, any questions on this, though? All right, going back. We were here. We were at integral. We still had the outer integral, 1 to 2, right? And then the inside, we have found the antiderivative, which was -1 over x y cosine of xy plus 1 over x squared sine of xy. No more plus c, but we'll have an evaluation bar. We are letting our y value go from 0 to pi, right? Then we'll be done, and then the dx. Gone. That's where we are. Now we plug in pi, and then we plug in 0. We subtract those answers. Then we're going to have another integral. Wait till we get to triple integrals, right? Then you're going to have an inner, and then a middle, and then an outer. So you just, you know, it's tedious, but okay. Here we go. Plugging in. I'm really hoping things get nice here. We'll see. All right, plug in pi for y. So I get -1 over x. Y is pi times cosine of pi x plus 1 over x squared. I didn't give myself enough room. 1 over x squared sine of pi x. Oh my God. I'm already thinking about me having to integrate that on the next step. And I'm not, pardon?
You're the one who chose the problem.
I did. But hold on, I'm going to make a very good point here in a second, all right? I want everyone to recognize, though, how bad this is looking, right? Because can you imagine having to integrate this? Right, like forget the pi's even there. You got 1 over x, or you got cosine pi x over x. How are you going to do that? Like this one looks, oh man, I don't know. This is looking scary. It's looking scary. Let's keep going though. Let's get to at least what's next. Is the next part good or no? Y is 0. What's cosine of 0? Because that becomes 0. Cosine 0, 1. So, oh, and that's 0 too. So that's gone. Okay, that's good. Plus, let me see, sine of 0? 0. Okay, so we're at least that part's not bad, right? Okay, but I still have a really shitty integral. Cosine of what?
Oh, there's a y.
Yeah, there, where?
No, I saw the y up front.
Oh, okay, yeah. This right here, this becomes a 1, but then that y saved me, right? Because that goes to 0. All right, so let's see where we are. It's not pretty. I am at integral 1 to 2 of, I'll put in parentheses, -1 over x Let me write it this way. Negative pi x, or pi over pi cosine pi x. I so don't want to do this that my hand won't let me write it down. Okay, that's the first term, right? That's this. Plus sine of pi x over x squared dx. Yes?
What if in the previous integration our bounds had 0 into it, so now we would be getting like 0 over, we would have undefined.
That would be an improper integral. So in Cal 2, we deal with improper integrals as well. And there is a mini exam that you will get where there will be a problem where you will have an improper integral in there. So you just have to deal with it the way you did in Cal 1 with improper integrals. You take a limit, and then you see what happens. Okay, do we all agree that this is not pretty, right? This is not pretty. And the thing that really made it bad was the fact that when we started out, we had an integration by parts right away, which made things really crappy, right? Wouldn't it have been nicer if when we went to go take the antiderivative of this, we did it with respect to x first? Because if we did it with respect to x first, then the y's would be constants, wouldn't they? And you wouldn't need integration by parts, would you? Are we allowed to do that? Are we allowed to choose which way to go? Well, Fubini's Theorem. So what are we doing right now? We're going, that's a big pause button right here. You know what? No, it's not a pause. We need the button that kills the program. We need to actually stop this. We're gonna surrender to this because we now realize that going the other way would have been better probably, all right? Fubini's theorem is actually the theorem that says we're allowed to do this. So the Fubini's theorem says that when you're looking at a double integral over R of some scalar function f of x, y with respect to area, that you can do inner integral with respect to x, or you can do inner integral with respect to y, your choice, so long as what? You're over a rectangle. If you're not over a rectangle, the theorem does not work. So you're allowed to change the order of integration if your region on the ground is a rectangle. So let's redo the problem using Fubini's theorem.
Are we going to get into like what happens if we do it the other way?
We just did it the other way and we didn't like it that way.
Like it's not a rectangle.
Oh yes, that's what. Yeah, that's where we're headed. Yeah, rectangles are the easiest things to integrate over. Everything is nice when there's rectangles. All right. So now rethinking this, and now equipped with Fubini's theorem, I can now rewrite it this way: 0 to pi, 1 to 2, y sine of xy, dx first, then dy. This is equal to the integral from 0 to pi, and then my outer integral is going to be with respect to y. And now I need to find the antiderivative of this with respect to x, treating y like a constant. So if it helps you, which I think for some of you this is confusing you, not helping you, this would be like me asking you to do this. 5 sine 5x dx, right? The y is like a constant. So if I asked you to find the antiderivative of this, you would pull that first 5 out the front like this. And then the antiderivative of that you could do with pretty basic u substitution. So this should become negative cosine of 5x plus c. That's your antiderivative. Do you all agree with that? Because if you take derivative of that, you get that. You had to scale this by 1/5 when you did the antiderivative, but then the 5 out there kind of kills off that 1/5. So we have the exact same answer as this, except instead of 5, we have y, don't we? Okay, so the antiderivative here is negative cosine of yx. I'm going to write xy because Why not? And then we're going to evaluate this from what variable?
1, 2, 1, 2, yeah.
X equals 1 to x equals 2. And then we'll do an, this is looking much better. Yes.
Will we not bring the y down too?
What the y what?
The y that's in front of the sign, will we not bring that down too?
It would, well, it's here, right? This is like the y and this is like the y.
Yeah, no, we said.
So you bring the y out. And then what's the antiderivative of that? It's negative 1 over y cosine of xy. Right? Because you have to scale out that constant. And then that 1 over y hits that one, and they go away. Look, I know Cal 2's been a while. If you're having any trouble with this, I would just, I'm not taking a bunch of time to this. Just go do it on the side. Take your time through it. It'll start to come back. All right. Are we good though? Okay. All right, now, x is 2, right? I'm going to plug in 2, then 1. So I've got this now. Integral 0 to pi. Okay, when I plug in 2 for x, I get negative cosine of 2y. And then I have minus, so that's what happens when I plug in 2. Then minus, now whatever I get when I plug in 1 for x, so now you just get minus cosine of just y. Minus, minus, plus. Any questions here? Next line. I'll go up a little bit more. Next line is negative cosine plus that, right? So I'm going to write it the other way. Cosine y minus cosine 2y, just so I can have a positive out there, dy. All right, I just flipped the order. And that right there I'm super happy about, right? This is just going to be sine y minus 1/2 sine 2y antiderivative. 0 to pi. X equals, sorry, y. I just said y equals 0, y equals pi. Yeah? Are we going to get 0? We're going to get 0. Man. So pi goes in here, sine of pi is 0. Pi goes in here, sine of 2 pi is 0. 0 goes in here, sine of 0, 0. It's 0. All of that for literally nothing, right? All of that for literally nothing.
What does the 0 volume look like?
Let's take a look, okay? Because this is actually an important result we got, right? What does 0 volume look like? Well, let's take a look at the picture. Do you all see how nice it was to do it this way as opposed to the other way? I would like to, after I show you the picture, I'd like to go to Wolfram Alpha. I'd like to type in the iterated integral the way we tried it initially, and I want to see what answer it gives us. It should give us 0, all right? All right, so the picture. Is there a question? Yeah.
Does that mean we solved the other complicated integral?
We did. The one we couldn't solve, we just solved. But we switched the order of integration, which made it an easier problem. So the moral of the story is, if you have a problem like this double integral over a rectangle, and you're having trouble with the integral in one order, you can maybe switch the order and it might be easier to do. So here was the surface. That was the surface. And we were trying to find the volume between the surface and the xy plane, right? So underneath that volume. So let me show you what that volume looks like. Let me show you the range. This is the image of that rectangle. Can you all see that part of it is above the xy plane and part of it is below? Let me take this out of here. Let me take that out. Let me take the surface out. Now, there's some problems with my code. It's cutting off over here because I told it not to calculate too many points because it'll take too long. So this actually comes down nice and smooth, and then the other part is underneath the xy plane, right? So we've got portions of this volume above the xy plane, and so the double integral counts that as a positive volume, and anything that's below the xy plane, it counts it as a negative volume. Just like in Cal 2, if you were to take, let's say, y equals sine x, and you were to do the integral of that from 0 to 2 pi, you'd be trying to find the area underneath that curve, right? And if you calculate this, you're going to get 0, because it's going to count that as plus and that as minus. And it just comes from the idea that when you're looking at these rectangles, right, the area of that rectangle is width times height. If your height is a positive number, your width is always positive. Two positives are positive. But here, your rectangle's down here, your height is a negative number. In the summation, it's a negative. And a negative times a positive is negative. So it doesn't know we're talking areas here, right? The formula just is taking the value of the function. It doesn't treat it as a height. So same thing's happening with our boxes. All of our boxes in here that we're drawing, the height of it is the value of the function at some points in the box, right? So if that point is above the xy plane, then that side's going to be positive. But if we're down here, then one of our sides of our box is going to be counted as negative in our formula. So the only way to truly figure this out, and this is actually a more profound question, is if we wanted to know the volume of the part that's above, right? Like over here, it's easy. What would we have to do to figure out like what's the volume of that, or sorry, area of that? We go from 0 to pi, right? Then we can find that. Does anyone know what the area of that is? It's crazy that it's 1.
No.
It's 1. It's weird. Doesn't seem like it should be that way, but it is. Here, what we would have to do is we'd have to figure out where it's above and where it's below. So I would have to kind of turn this, and I would have to say, look, between like that is the region where it's above, right? So you would have to define that, and notice it's not a rectangle anymore. So how do we do that? Well, that's what the next section's about, all right? Yes?
Couldn't we also apply a vertical shift and move it up above our axis so that no one has a negative? If we just
No.
find how far below it goes, we can...
No, because this is relative to the xy plane, which is really like, again, when you go back to Cal 2, when we do this, right? When we do that and we try and find that area, what we're really doing is we're saying the f function on top is this function, and we're counting the bottom function, which is our g function, as 0.
Right.
And so if you shift, your g is going to have to shift as well. Yeah. Hold on. Fubini's, okay. We have a special case. What's your question?
So wouldn't it also be 0 if there's only a singular point being intersected within that box that we look at? So let's say, for example, a plane were to hit it at one singular point and then it would bounce off whatever is in that area that we look at. So the bounds that we have would be only one spot. No?
I just don't understand the question.
That's
Yeah, try and rethink it, and then maybe
we're looking at bounds.
speak up so everyone can hear you.
So we're looking at bounds.
Okay? Yes?
And then our plane ends up, or whatever shape we have, ends up just intersecting between those two bounds at a singular point. Would that still be a 0 volume?
So you're saying you have a surface that intersects, it comes down to your plane at a single point, and the rest of it is above the x-axis? And you're saying then the volume would be?
Not above the x-axis, but above our bounds. So our bounds between our y and our x, we have our square. We have our
Yeah.
rectangular bounds.
Okay? You have a box on the ground?
And then we're looking also at the y. We also have another box, right? That extends that height. So we have a volume that we're looking within our area, right? Right?
We have a surface now
Yes, now
above
our
this.
surface within our bounds is just touching the singular point within the bounds that we're looking at. Is that still 0 volume?
Our surface is touching a single point within the bounds. You mean on that plane?
Sure. Yes.
No, not sure.
I don't know how else to explain it other than like.
I can't answer it if you can't explain it in a way that I can understand it.
We can go ahead
Okay, all right. I'm trying, I don't understand the question. Okay. All right, so a special case, all right, so look at this function of x and y. This is a very special case. We can only do this when we see this, where our function of x and y is a function of x multiplied by a function of y. That means you can separate it into two factors where one of them just has x's, the other one just has y's. Looking at the problem we just did, we just did that problem, right? Can you look at this as a product of two functions, one that only has y's and one that only has x's? No, right? Because there's your product, right? Right there. That one has just y's in it, but this one has x's and y's, and there's no way to split that up and to separate them. So this would not qualify for this theorem. I'm going to show you an example that you can, but what does the theorem say? It says if you have this situation, then when you're trying to do this double integral over R with respect to area, what you can do is you can just split it into two separate integrals and multiply them together. The first integral is just the one that has the x stuff in it, and the second integral is the one that has the y stuff in it. And then the limits of integration are the limits for x and y respectively. Let's do an example, right? So we have this function of x and y. The function of x and y we have, yes?
Does this still only work if it's under a rectangle?
Yep, we're all still on a rectangle right now. Oh, but would this theorem work on it? Actually, this will extend. This theorem extends out. So if you have a function of x and a function of y separated by multiplication, no matter what you're integrating over, you can separate it into two. Yes. The only thing we can't do is Fubini's. Fubini's, we can't switch the order of integration unless we have to be over a rectangle. Good question. All right, so do y'all see that we have two functions here? Like separated, there's multiplication. This is some function of just x. This right here, h of y, is a function completely of y, right? And they're separated with multiplication. So this theorem applies. So the theorem says that, okay, all we have to do this double integral over R of sine x cosine y dA is to split it into two integrals. The first integral will be the one with x, so 0 to pi over 2 of sine x dx times, and then the other one also goes from 0 to pi over 2, but this one is the cosine y dy. And you don't have to worry about inner, outer, or anything like that. You just treat these two integrals separately. Take the two answers, multiply the answers, you're done. Dot, dot, dot. I won't finish that off. I think those are pretty straightforward. This is the picture. There's the picture, and so we are finding the volume under there. Okay? Yes?
This also works like when you can division of two functions.
Well, it works as division, but then you would look at the other one, like let's say it was like over something, you would look at this one as 1 over that, right? So you could split it into a product. Okay. Properties of double integrals. All the things that you think double integrals would do, they do. Like everything that you had in Cal 2, you have in this double integral. You can take the double integral of the sum or difference of two functions, you can split that into two different double integrals. You're completely allowed to do that. Just like this has been the story since differentiation, right? If you're taking derivatives of sums and products, you can split it up and take derivative of each one. When you're doing antiderivatives of sums, did I say sums and products? I did. Sums and differences. I said sums and products. If you're differentiating sums and differences, you can differentiate each one by one, or same thing with antiderivatives. With double integrals, the same thing applies, all right? Also, constants can come out front, okay? Which we were doing, but we were doing it like within the inner integral, we were pulling out constants. We can always pull constants out at the very beginning of a double integral. It can just come out, boom, all right? Also, if you have some function of x and y that's bigger than or equal to some other function of x and y. So you've got some surface that's above or equal to some other surface. Then if you do the double integral of this one, the volume of that should be bigger or equal to the volume of this, which I think makes a lot of sense, right? This one's above that one, so the volume of that one should be more than the volume of that one. All right, and we're at the final note for this, the volume between two surfaces. So the analogy here, going back to Cal 2 again, is that, you know, we first start by looking at some function f and we look at the area underneath it, right? Between a and b. And then after that, we say, what if you bring another function in here like g? And now what you want to do is you want to find the area between them. Then all you have to do is subtract the bottom one from the top one. And that's exactly what this note says. If you're given two surfaces, okay, f of xy and g of xy, over a rectangle, then the volume between them is this. You just take the top surface and subtract the bottom surface. So I have a picture that goes with this that you can see. Hopefully that makes sense. You have a top surface. You have a bottom surface. You have the rectangle on the ground. You want the volume between those two surfaces. Then you set up that double integral over that rectangle. And then what you do is you take the f function, you subtract the g function with respect to area, and that'll give you the volume between them. Yes?
Why is that limited to only rectangles?
This is not limited to rectangles. Now, when we get to the next section, we're just going to have another note that says this is how we do it, like difference, like if we want to find the volume between. The only thing we cannot take into the next sections is the Fubini's, the changing the order of integration. We can't do that. Yeah?
Are we allowed to split the integral into two non-overlapping like regions?
Mm-hmm. I think what you're asking is like, let's say we had this rectangle. Could we split that rectangle into two rectangles?
There's like an asymptote
Sure.
region.
Yeah, you can break it up. Yep. Now, we won't have anything like that, but you could. All right, got the idea? Yeah? Okay, let's move on to the next section then, which naturally would be, what if it's not a rectangle, right, on the ground? So, double integrals over general regions. So we already did this, right? We have a region, R. You could say region, R region, or you could think rectangle here. X is between two constants, Y between two constants. We've got that covered, right? We know how to do that. But what about if it's not that, right? Well, it could be a lot of things, couldn't it? I mean, if it's not a rectangle, it could be a ton of other different shapes. So we're going to start by looking at two specific types. These are not the only types, but we got to start somewhere. Our first type region is a region that looks like this. Now, I don't want to show you the picture yet. I want you to just look at this, and then we're going to talk. We're going to hopefully see if we can kind of extrapolate what it's saying. So the domain, the part on the ground, is no longer a rectangle. What it is it's all the points x and y that satisfy these two conditions. First, the x is trapped between two constants. So that's the same, right? Your x is trapped between two constants. And that's the mathematical symbol for and. And what? Your y is trapped between two different functions of x. So we're talking like this. We're looking at the ground, right? So instead of having a rectangle on the ground, instead of that, what we have is this. We have that our x's are trapped between two constants, right? So our x's are trapped between here and here. But our y values are actually stuck between two functions of x, which means that we have some function of x like this. Let's call that g sub 1. And then some other function of x here, g sub 2. And so the region we're actually looking at looks like this. Okay? We call this D for domain, all right? the domain here of this type 1 region, x is between two constants, y is between two functions of x. That's just a better picture. So how do we do these? Well, here's how it has to be done. To do the double integral over d, not sure why that d is off to the side here, f of x, y, right, of the function with respect to area, we have an outer integral and an inner integral. The outer integral has the restriction a and b, and it's with respect to x. So your outer integral is the restriction between the constants. The inner integral is with respect to y, and it is trapped between, the limits of integration are the two functions of x that you have. That's a better picture. So let's say the region on the ground, our x's are trapped between two constants. Our y's are trapped between two functions of x. And now look, we have an upper surface and a lower surface, right? We want to find the volume between those two. Then we would subtract the two, right? We'd subtract the f minus g, but the integral would be outer integral with respect to x, inner integral with respect to y. You have to go in that order. No switching, no Fubini's theorem here. Example, right? This is a type 1 region. There are 67 type regions. I'm kidding. There's type 1, type 2, and then we start getting into polar coordinates, which in three-dimensional space will become cylindrical coordinates, then we get into spherical coordinates. So we try and handle as many types of weird regions as we can. Right now we're working on ones where our x's are stuck between two parallel lines and our y's are like wavy. All right, so find the volume under z equals x plus 2y on the region bounded by y equals 2x squared and y equals 1 plus x squared. It doesn't look like I've given you a domain for x, does it? But maybe when we draw the picture, there will be one. So let's see here. Do we all see that this right here, this is our f of x, y? This is our surface, right? Which actually, what is that? If you were to sketch that, what would that be? A plane. That's a plane, right? Because you've got x, y, z all in one equation. They're all raised to the first power. It's a linear equation in x, y, z, which is a plane. So that's a plane. So we got some plane, right? And we're trying to find the volume below that plane down to the xy plane.